Welcome to this video on digital electronics. In this video, which is the second in the series of combination logic circuits, we will be discussing about parallel adders. We look into ripple carry adders and carry look ahead adders. We will also be discussing on parallel subtractors and Bcd adders. First, parallel adders or ripple carry adders. So they are used for adding n bits of two binary numbers. As indicated here, a and b are two binary numbers that are to be added and they have n bits each. So a0 through an minus 1 and b0 to bn minus 1. So both the binary numbers are to be added. So we proceed adding with each of the bit positions, a0 with b0 and then a1 with b1 along with the carry generated in the previous state, and then a2 with b2 and the previous carry generated and so on. So as indicated in the block diagram, for an n bit parallel binary adder, n full adders are required and they are connected in cascade. Now for the first adder, carry input is given as 0, or for the first adder half adders can be used. We know a full adder, three inputs are given, A, B and the carry input, and the outputs are sum and carry. So the carry of output of each full adder is given to the carry in of the next stage. And so A, B, the two bits plus the carry is added and we get the sum and carry which is given to the next stage. The next stage, the next two bits A1, B1 are added and we have the sum and carry out which is given. So this goes on till the n minus 1 stage, and totally we get the sum and the carry output and the final result of sum. So if Tp is the propagation delay of carry in each stage of full adder, then the total propagation delay is n times Tp if we have n stages of adders. So the total output is available after the time of n Tp. Next, let us have a look at the 4-bit parallel binary adders. So as given here, the augment and the addend are A and B with 4 bits each, A0, A1, A2, A3 and B0, B1, B2, B3. On addition, first A0, B0 with the carry 0 which is made 0 is added. We get the sum as 0 and the carry 1. So sum 0. Carry goes to the next stage and it is added with A1 and B1. We get sum 1 and carry 2. And carry 2 is given to the next stage. So this goes on. At the final stage, A3, B3 and C3 are added in the final adders, A3, B3 with the carry C3. We get sum S3 and carry C4. So sum S3 and carry C4 which is taken as the result. So IC7483 is a 4-bit binary parallel adder. And this is also called a ripple carry adder because the carry gets rippled from one stage to the next stage. Next, going on to 4-bit parallel binary subtractor. We have already seen in the video on binary arithmetic for addition and subtraction that subtraction A minus B can be represented as A plus minus B, and minus B 2's complement can be taken. So taking 2's complement of the subtrahend, addition operation can be performed. So to take 2's complement of subtrahend, it is taking 1's complement and adding a 1 to the LSB. So here all the bits of the subtrahend are complemented and the carry 0, a 1 is given. So that gives us the 2's complement, and the same adder circuit can be used for subtraction as well. So as shown in this block diagram, full adders are used. A0, A1, A2, A3 are the minuends that are given as inputs, and the subtrahend needs to be complemented, 2's complement. So that is 1's complement of the subtrahend, that is complement each of the bits and add a 1 to the LSB. So each of the bit is inverted and given for subtraction purpose, and to the LSB the carry is made 1. So we have this adder operating as a subtractor and giving the difference with the borrow as the result. Now to design a single circuit which will function both as an adder and subtractor, we have a 4-bit binary adder subtractor. So here we give an additional line m is equal to 0 or 1. If addition operation is to be performed, m is given the value 0. If subtraction is to be performed, it is given a value 1. So, we will see how a parallel adder circuit can be used for both addition and subtraction. So, XOR gates are given and the M control line which decides whether it is going to be an addition or subtraction line is given as an input to each of the XOR gates, and the other input is the subtrahend or the addend that is given. Let us see how it goes on. So, an XOR gate, we already know the operation, the truth table of which is given. If M and X are two inputs and Y is output, this is the output for an XOR gate. So, here M is the input line that we give, either a 0 or 1. So, we see if M is 0, then the output is the value of X. So, 0, 0, 1, 1. Whereas, when M is 1, the complement of the other input is obtained as the output. If X is 0, we get Y is 1, and X is 1, Y is 0. That is, so when M is 1, the output is X bar, and when M is 0, the output is X. So, to this XOR gate, when addition should be performed, 0 is given as one of the inputs to each of the XOR gates, and the other is the number that should be added, that is the addend. So, the output that we get is the addend as such. So, we see when M is 0, the output is X. So, the output is B naught as such. So, addition is performed by this circuit. Now, when M is 1, that is 1 is given to one of the input lines of each of the XOR gates, we see the output when M is 1 is X bar, the complement of the input. So, what we get the output is B naught dash, B1 dash, B2 dash and B3 dash over here. And this line is 1, and that is given as the carry input to the first stage. So, effectively 2's complement of the number has been obtained. The adder circuit is used to perform subtraction. So, we have used a single adder circuit to perform both addition and subtraction. We have seen in the previous parallel adder circuits that the carry has to propagate from one full adder to the other, and for the final result to be available, it is n times the propagation delay of each full adder, and therefore, there is a delay in the total operation and the result to be available. If each of the numbers have large number of bits, then the total delay becomes large. So, these adders, parallel or ripple carry adder, have carry propagation delay. So, to overcome this problem, there are many methods available, but one of the most popular method is using a carry look ahead adder. So, here we anticipate the carry and take it in advance. So, it is based on the principle of looking at the lower order bits to take the carry. So, instead of looking at the previous bits for the carry, the higher order bits can get the carry from the lower order bits in the number. So, let us see how we can proceed with this method. This is a truth table for a full adder, which we have already seen, where A, B and C are the inputs and sum and carry are the outputs. If you closely observe, when A and B, the two inputs are 0, the output carry is 0 irrespective of what the input carry is. So, when A and B are both 0, irrespective of the value of the carry input, carry output is 0. That is, no carry is generated. Now, look at the next 4 combinations. When either A or B, one of them are 1, then whatever is the carry, that gets propagated out as the output carry. You can see 0 becomes 0, 1 is 1, 0 is 0, 1 is 1. So, that is carry propagation occurs. Carry out is equal to the carry in. So, this is carry propagation or indicated by the symbol Pi. And the next combination, when both inputs A and B are 1, irrespective of the value of carry in, whether it is 0 or 1, carry output is generated. That is, when both A and B inputs are 1, a carry is generated irrespective of the value of carry in. So, that is called carry generation, or carry is 1 and the symbol is Gi. So, when A and B are both zeros, there is no carry generation. When A and B are both ones, carry is generated, and when either of them are 1, carry gets propagated from the input to the output. So, this is the principle that is used for designing a carry look ahead adder. So the two functions that are performed are carry generation gi, which is equal to aibi, and carry propagate. Observe the suffix I gives the stage number. For a given stage, the carry generate and propagate depend only on the values of the inputs a and b. This is the logic diagram that we have seen for a full adder, and the output from the XOR gate is the carry propagate pi, and from the AND gate is the carry generate gi. So the sum is XOR of carry propagate and the carry input, and the carry that is generated output is gi, carry generate plus propagate into ci, and this carry propagate decides whether a carry from the input is getting propagated. Ci goes to Ci plus 1. Now looking a little further into these expressions. So we have the sum carry propagate generate sum and carry that are given here. Considering the carry Ci plus 1 is Gi plus PICA that we got. Consider the initial carry to be C0. For the next stage, if I is 0, substituting in this expression, we get C0 plus 1 is equal to G0 plus P0 C0, and that is C1 is equal to carry generate plus propagate and carry of the previous stage. Okay, so this is the first stage, carry of the first stage. Carry of the next stage, substituting I is equal to 1, we get C2 is equal to G1 plus P1 C1. Substituting value of C1 from the previous expression and simplifying, we get C2 is this expression. Note in this expression there is no value of C1, only value of C0, carry 0 is there, and G0 and G and P are the inputs available A and B. Next, for I is equal to 2, we get carry 3. So G2 plus P2 C2, substitute the value of C2 from the previous expression and simplify, expand it. We see here again C3, carry 3 also depends only on carry 0. So it is observed that carry C3 can be generated at the same time as C2 and C1 because its value depends only on the current inputs and the previous carry of only C0. So any stage, n stage, for calculating the carry, the previous stage carry is not required. C0, knowledge of C0 is sufficient. So carry can be generated simultaneously in all the stages. So this is carry look ahead adder. So implementing the expressions that we have seen in a logic diagram, this is a logic diagram of a carry look ahead adder. So C0, G0, P0 gives the first carry, and then C0 plus the other combinations gives the second carry, and so on. So using that logic mentioned earlier, we have the IC 74182, which is a carry look ahead generator. So giving the inputs as P3, G3 and so on, and the outputs are the carries that are got. So from this, the sum and carry can be obtained, the addition numbers. So we have already seen the carry propagate can be obtained by XOR of the corresponding bits and carry generate from the AND of the corresponding bits. So these are all given as the input to the IC, and the output we get the carries, and carries XORed with the carry propagate we get the sum that resulted. So the carry look ahead adder, simultaneously the result is available for any number of bits. So this is an example of a 4-bit carry look ahead adder. Next, moving on to BCD adders. As we have seen in the video for binary arithmetic, in a BCD adder, BCD where the numbers from 0 to 9 are only valid. So any addition which results in a number greater than 9, a correction has to be done because it's an invalid BCD number. So when the sum is greater than 9, or if a carry is generated which indicates that it is an invalid BCD, a 6 has to be added to convert it to the correct BCD. So we shall obtain the logic diagram to check if a number is greater than 9. The inputs for 4 bits which represents a BCD number. So 4 bits are used. So all the combinations, possible combinations using 4 bits are from 00 to 111. But a BCD number is valid only up to 101, that is decimal 9. the numbers above them are invalid BCD numbers. So let us have an output of 0 for valid BCD numbers and indicate a 1 for invalid BCD numbers. Now draw a K-map for these inputs. So we have 4 inputs, a 16 variable K-map. Solving the expression, we get y is equal to S3 S2 plus S3 S1. So implementing this in a logic circuit, we can get a BCD adder. Using a 4-bit binary adder, 2 BCD numbers are added. The resultant, if it results in a number less than 9, the result is valid. If it is greater than 9, we have seen a 6 has to be added. So the logic we had obtained for when a number is greater than 9, so implementing that logic is a combination circuit. So either when a carry is generated from the first binary adder, or if a 1 is generated out of the logic when a binary number result is greater than 9, this output carry becomes 1. So giving that as an input to the second binary adder, so it is given to the middle bits, 2 bits. So this represents 0, 1, 1, 0, that is 6. So a 6 is added to the binary number that is obtained and the correction is made and we get a valid BCD number with a carry. So in this video, we have seen addition of 2 binary numbers with n bits each using ripple carry adder as well as carry look ahead adders. We have seen how a parallel binary adder circuit can be used for both addition and subtraction purpose. And then we have discussed about BCD adders. These are the references. Thank you.